Hi guys. In this video, I want to talk to you about springs and essentially how to model the force on a spring. So we haven't dealt with it so far in too much depth, but we have talked about how to model forces, just generally speaking. I want to point your attention to this video that we used for a previous lab. It was using this setup of variety of masses to determine, to get an equation for the force of gravity. In this experiment, you had something that measured the force, and then we changed something. Like, what do we think affects the force of gravity? In this case, it's probably the mass. So that's kind of what we did. That's what I did and recorded. As we added more mass, you see on the left here, the force of gravity increases. And really the thing we're trying to figure out is, what is the shape of this graph? Is it parabolic? Is it a line? And when I say the graph, I mean force of gravity on the y-axis, and the thing you're changing, in this case, mass, on the x-axis. And what we would see if we were to kind of plot this or review back to our results, I would get something like essentially a straight line. And the slope on this straight line was about 9.8 newtons for every kilogram. So we turn that graph into an equation, slope of 9.8 newtons per kilogram times the mass. This was our equation for gravity. Fg is equal to mg. It didn't really just pop out like this though, because you need to do a certain amount of interpretation. So like, what if the slope here was steeper? Like, what would that mean? What is the meaning of this 9.8 newtons per kilogram? If you unpack the per, you say, a steeper slope of, let's say, 100 newtons for every kilogram. What does that mean? It means if I have 1 kilogram of mass, the force of gravity on it would be about 100 newtons. So that's kind of the distinction there. Let me just rewind a second. So in blue, I have that steeper slope, and what the steeper slope on this particular graph would mean would be essentially like if I was on a different planet, let's say Jupiter. I wouldn't expect that a 1 kilogram object would be pulled by the planet by 10 newtons. On Jupiter, it's much, much greater. So that's kind of how we model the force. Change something, create that graph, interpret the slope. And so that's what we're going to kind of look at for a spring. So the setup is like this. You can see that this is the thing that's measuring the force. And this right here is a very thin spring, and you have a variety of springs. So you can even change some stuff. But the thing that I want to focus on in this particular setup is, what might affect the force exerted by a spring. If you ever played with a rubber band, hey, something that might make sense to change is the stretch. If I stretch it like this versus stretching it like this, how does the force compare? We can measure that if we put down a ruler. Let's say it starts off at that point, and I can measure the change. And I can make, a graph of force versus stretch. You can see that this spring 5, it requires about 2 newtons of force to be stretched, maybe 30 centimeters. 2 newtons of force, 30 centimeters. Whereas spring 1 requires about 4 newtons of force to be stretched 12 centimeters. So, there's some slight differences between these springs. Let's talk about what the graph would look like if it actually is nice enough to kind of have a sample set of data. And here it is. So I believe this is the force on spring 1. The stretch, how much the spring is stretched, is on the x-axis, and then the force exerted on that force scale is on the y-axis. So you're seeing here the shape of the graph is linear. And I'm going to make up a value of the slope. Let's say it's about 0.3. So 0.3 newtons for every centimeter. Can you pause the video and try to interpret what does that 0.3 represent? What would a larger slope of, let's say, 10 newtons for every centimeter, what would that mean? Pause the video, think it through, and we'll talk about it. Hopefully pause the video, hopefully you thought about it. That 0.3 in this case means 0.3 newtons of force needed to stretch the spring 1 centimeter. And so if I had another spring and I did this experiment and I got a slope of 10, that would mean to stretch the spring 1 centimeter, I would need to exert 10 newtons of force. So in this case, the larger the slope, the harder it is to stretch. That's the key idea, and I'll talk about that more in the whiteboard. Okay, so let's unpack that a little bit. The shape of the graph, force of the spring, x here is the stretch. What we saw was that it was roughly linear, not square root, not parabolic, linear. So if I want to look at this, turn it into an equation, I can say Fs is equal to the slope times x, x again being the stretch, F sub s is the force of the spring. And so this slope is what we give it the term K. It basically is just this number depends on the actual spring. So some springs are easy to stretch. They have a small K value, a small slope. Some springs are hard to stretch. I got to put a lot of force and it's not going to stretch very much. So that would be a larger slope. That is this K. K is called the spring constant, and it is larger. I'll say intuitively, it's how hard it is to stretch the spring. Okay, so there's some other things, just two more things I wanted to highlight. This equation, f sub x, this is how I'd like to write it with absolute value signs. Why absolute value signs? Where did my rubber band go? Pause. Rubber band, voila. So you can see that when let me keep my hand here still. When I pull it in this direction, the force on my hand is in the opposite direction. So that's how springs tend to behave. If this was something that I could compress, like a ballpoint pen, when I compress it, the spring pushes outwards. So there's really, if you were to model this, there's a negative sign in there. So you might see it like that sometimes. On the Regents reference table, it is just like this. But sometimes there's that negative sign because the spring wants to basically restore itself. If you stretch it, it wants to get back to equilibrium. If you compress it, it wants to get back to its natural state. We're not going to really worry about that. I just want to mention it. This equation is called Hooke's law. It's not really a law in physics. It's kind of just a experimentally verified thing. A lot of materials behave like this. The force needed to compress them, it is linear up to a certain point. If you were to keep stretching this rubber band, at a certain point it's going to break. For a spring, after a certain point, it's going to deform. So just some added details. Key idea, this is called Hooke's law. And it says essentially that if I double the stretch, I double the force needed. And that's different than gravity, right? Well, if you can see, if I had something that was hanging on this, let's say this rubber band or this spring, the force on it would be changing constantly. As the stretch changes, the force would change. So it's not a very simple force. Whereas if I just drop this, gravity's pulling on that the same throughout. Okay, there's one other thing I wanted to highlight on this force versus stretch graph, and it is that if I was to sort of replace this y-axis with this brand new equation I got, the area here is important. This is a triangle, so the area of it is 1/2 base times height. And in this case, the base is x, and the height is kx. So the area here is 1/2 kx squared. Hopefully you can recognize this. The area under a force versus a spring force versus x graph is 1/2 kx squared, the potential energy stored in the spring. Potential energy of spring. So this is just something that we'll see later on. The area under a force versus displacement graph, it turns out to correspond to a change in energy. And we'll talk about that more. Hopefully that was helpful. See you.